So, so good evening to all of you. And on behalf of the physics department, I welcome Professor Nityanand for this talk. And we are grateful that you accepted our invitation and you agree for this popular level talk. So let me brief about the department at Pilani campus. So in Pilani campus, presently we have 20 faculty members who work in different areas of physics, namely condensed matter physics. The largest faculty members work in this area. And then atomic and molecular physics, optics and spectroscopy, and high energy physics, and cosmology, and early universe, and so on, astrophysics, and so on. And presently, we have 30 PhD students, and we have two more departments in Goa and Hyderabad, and altogether, if we add roughly 50 to 60 faculties members we have. So with this, I stop now, and I invite Professor Tapome Guasakas to introduce the speaker to all of you. So over to Tapome Guasaka.
All right. So, okay. So there's not much to introduce here. Professor Nityananda is one of the people in the community of physicists in India who probably most of us know. But for young PhD students, I think it's important to know about his accomplishments. So Professor Nityananda originally interestingly worked in the area of solid state physics and crystallography before moving into theoretical aspects of astronomy. So in RRI, and he has a long, cherished and very interesting journey of research and profound contribution to physics as an astronomer. So he was the director of the NCRA, the National Center for Radio Astrophysics in Pune, TIFR. He retired in 2013, but he has been teaching ever since at IISER Pune and also Azim Premji University in Bangalore. He's members of the three science academies in India and has served as the editor of several Indian astronomy journals of the Indian Academy of Sciences. I think he was also the chief editor of Resonance, and his research is very diverse in various aspects of optics, astronomy, radio astronomy. Apart from that, I mean, I have always known him as one of the best teachers that we have. My personal interaction with him happened about I think about a decade back when I was in NCRA in the radio astronomy school, where he taught us introductory radio astronomy. So Professor Rajaram is full of anecdotes, and we have already seen glimpses of his sense of humor, which has always been something which has enriched his class. So thanks again, Professor Rajaram, to accept our invitation and deliver this talk.
Thanks, Tapaway. Thanks to the whole department for hosting me. So let me.
May I interrupt, Professor Rajan?
Yes.
So, for this lecture, you please first complete the lecture, and at the end of the lecture, when the lecture will be over, so we will invite audience if they have any doubts, so they can raise their hands, and I will pass their doubts to you so that you can address their queries. Will it be okay?
Surely. I mean, that's the standard practice, I think.
Okay.
All
Okay.
lecture.
Thank you. Okay. Thank you.
Thank you. Okay. So, very general title, and even the abstract maybe made it a little more specific. So I have chosen to bring optics to the forefront, but the context will be astronomical. And to make it broad, I'll also be covering different areas. And I'm going to start with what many people think is a sort of neglected and boring part of optics, namely geometrical optics. Okay, and we'll see that well into the 20th century, very interesting applications of geometrical optics were made in astronomy. And I'm not referring to what's done in the telescopes, but what is happening in the universe. Okay, so we'll start with that. Then we'll move on to some wave optics and some quantum optics. That's my overall plan. Oops, I think I stopped sharing, which I should not have. So let me plunge straight away into a phenomenon known as gravitational lensing. And I'm just going to show a few examples of it first and then discuss a little bit of the theory, which is a bit interesting. So this is a phenomenon. If you look at the vertical axis, it's the brightness of a star. And interestingly, the way astronomers measure brightness, if this number goes down, it means that the star is getting brighter. Okay, and you see this very interesting kind of very symmetric curve. Oops. And you can also see that this event of brightening, incidentally, in magnitude, there is some, 1.5 magnitude. So, maybe a factor of 3 or so. But this itself is part of a bigger peak. Okay. Now, of course, stars vary in brightness due to many reasons. But this particular one is because some object which is otherwise unseen has passed in front of the star. And you could loosely say focused the radiation. So this kind of event, just a smooth up and down, is quite common. Of course, once one looks for it. I should say that looking for it means monitoring the brightness of millions of stars. And then every few weeks, you may pick up one event like this. But this is special because in addition to the star causing this, it looks like some planet around the star has caused this. Okay? So this is a very contemporary application of this accidental focusing of rays. Now, this is an example on a slightly bigger scale. This is a somewhat nearby galaxy, and it's surrounded by 4 images. Again, this is one, to find one like this, people had to study thousands of cases. This goes by the name of Einstein Cross. Now, the interesting thing is that these are 4 images of the same object because they have the same kind of spectrum, and all kinds of tests have been carried out to verify that it's a single object behind, but the rays are being bent in such a way that it's reaching you by 4 different parts. And here is on an even grander scale. So earlier we had seen one galaxy. Now this is a cluster of galaxies. So each one of these is a galaxy in front. And then these were observed in 1980s, but people didn't understand it at that time. You saw these giant arc-like features. And this is not the only feature. You can see some arc here, some arc here. Turns out that when it's properly modeled, these galaxies are in the foreground, and there is a single galaxy quite far away whose light is being bent. And now this is on a much grander scale. That was on the scale of arc seconds. This is on the scale of arc minutes. Okay. So this is the context of gravitational lensing. And so I would like to start thinking of this in terms of wavefronts. Even though this is geometrical optics, you can always draw these surfaces called wavefronts, and the rays are perpendicular to the wavefronts. And one very simple way of thinking of wavefront is, let us say this is the background object. And especially in astronomy, sometimes objects explode, right? You can have a supernova which suddenly increases and decreases in brightness. So that message will now be carried on a spherical wavefront. It will keep traveling, and let us say it then encounters something like this cluster of galaxies. I've just shown it as a kind of gravitational potential value. So what happens when this wavefront passes? Of course, the parts of the wavefront which pass very far away from this object are unaffected. But the part which passes through this object is delayed. Now, many of you must have heard that Einstein's general theory of relativity predicts something called deflection of light. But once you think in terms of wavefronts, this deflection and delay are really closely connected, right? Because if you draw a normal to this wavefront, it's pointing in this direction. If you draw a normal to this wavefront, is pointing down. So the direction of the light is clearly changed. Okay, deflection and delay are just two sides of the same coin. In fact, I've just put down the famous Einstein formula for deflection by a point mass. So it has this length associated with the mass, which is Schwarzschild radius. So for the sun, 3 kilometers. And then you divide it by this impact parameter B. Impact parameter being the distance by which the ray passes away from the center. And once you have a formula for deflection for one mass, if the deflection is small, you can superpose. But you can also infer the time delay by saying what function do you have to differentiate. Okay? After all, you're looking at the slope of this wavefront to find out the direction of the ray, and it'll be log B. So actually, this is, of course, this is not a point mass, right? It's a superposition of many point masses, possibly even dark matter. So, okay, so now we have an observer, traditionally represented by an eye. What is this observer going to see? So one way of doing it is to draw the normals to this wavefront, and now that it has passed the gravitational potential, these normals will be the rays, and see, some of the rays will miss the observer and some of the rays will hit the observer. That's one way of doing it. But one way of tracing these rays is to now start in reverse direction. Imagine the observer sends out a wavefront. So this is now in dotted lines, a surface, right, where the normals to the surface automatically point to the observer, right? Because it's a wavefront coming from the observer. So then you want to just look at the place where the normal to this surface and the normal to this surface coincide, which means wherever these two surfaces are tangent to each other. So here's the first example. They're tangent here. Therefore, you'll definitely get one image from here. Right? By the way, this is not a perfect lens. Huh? In a perfect lens, all of the rays would come here. But that's not the only place, right? We can draw these wavefronts of different radius. So here's the next one, which is tangent at this point, and therefore you get a second image coming from here. And notice that these will not arrive at the same time. Right? This will arrive first. See, because this radius is larger, this will arrive later. And actually, there's even one more. Right? Yeah, there it is. So this geometric construction enables you to locate, in this case, these three images. But I'd like to go back and tell you that what we have kind of rediscovered is nothing but the Fermat principle of least time. Okay. So if you look at this ray, which is coming from here, clearly neighboring rays will have to travel more time because these two surfaces are tangent to each other, right? So in fact, the separation between these two surfaces can be called the time delay function. Right? And we would have a time delay function even if there was no gravitational lens, right? We would just have a curve like this. I mean, for small angles, both these curves would be quadratic in this transverse coordinate, right? So you have the difference between two quadratic functions is again a quadratic function. So that will have a unique minimum. So under normal conditions, you see only one image. But once you have introduced this gravitational time delay, you can get more images. Okay. So let's follow this up a little bit. So what we saw on the previous thing is just sketched here. Of course, now we are just looking along one dimension. This is the transverse coordinate. That is the sky, essentially the sky. So this is the time delay function. So you see that you can have two minima and one maximum. If you're very symmetric, if the lens is symmetric and all the observer, the center of the lens, and the source are all aligned, then actually you do see the central image, but this pair of images is just part of a ring, because this figure can now be rotated about this axis of symmetry. So that's called the Einstein ring, because Einstein worked this out for a point mass. But of course, this is unusual. If the observer moves away from that, it moves a little bit. One of these maxima goes up, one comes down. But if you move far away, you will go back to a situation where you have only one. So just to go back, if we had moved this observer somewhere here, you might have had only one point of contact between these two surfaces. Right? Now, of course, I've oversimplified, because really you should think of the problem in 2 dimensions, right? The 2 dimensions of the sky. But you have a geometric time delay, which is just theta squared. You have this gravitational time delay, which is for point mass log of theta, but in general, we've talked of the Einstein ring. But it's useful to think of first creating an Einstein ring and then breaking it up, either by the observing moving from the axis, or maybe if the lens is a galaxy, it's not symmetric. The lens potential might have higher multipoles. The next one is a quadrupole, for example. So I'll just give you a glimpse of what happens in this more general case. And just even these general principles, that we have a time delay function which asymptotically is quadratic, and then as you come near the lens, it can have a more complicated shape. You want to know which are the maxima, minima, and in 2 dimensions you can also have saddle points, and these are your images. Okay. So, for example, one of the things which follows from the mathematics is that you can get an odd number of images, which is what we have seen. The point mass is an exception because it's singular. When in this kind of argument, one assumes things to be smooth, point mass always produces 2 images, or a ring, of course. So, just a glimpse of what happens in a more general case, and I've quoted in case someone wants to follow up. This is one of the early influential papers in 1986, ABJ, which does it in 2 dimensions using Fermat's principle. I haven't talked about the intensity, and it turns out that the intensity is a maximum when 2 images are almost merging with each other. Actually, you can verify this for yourself in the kitchen by just taking a stainless steel plate and looking at a bulb on the roof and tilting the plate around. You can see multiple images moving around, getting brighter as they move. So I've just referred to one original paper and one review article. And the next figure, in the original paper did not have much to say about these arcs, but the arcs are a very spectacular consequence. So this is just what's been done is first you plot only the geometric time delay. So there's no extra potential, no delay, nothing. I have to apologize for these other strange rings here, which are not intentional. They are the result of one PDF maybe being sampled in another way when I copied it. And then some of you may know that when you have 2 incommensurate samples, you get these fringes. But please ignore them. Just look at the contour lines. So this is a simple quadratic function with a minimum, right? Then you introduce this extra time delay, right? Right. So it is distorted, but you still have only one minimum. But if you keep increasing it, we saw the case when there were 3, right? But now in 2 dimensions, you can actually draw the contours of this time delay function, right? So I think the best way to imagine this is as some kind of valley, and then someone is trying to push up a hill in the middle of that valley, right? That's the extra gravitational time delay. The moment you push up the hill has reached some height. Of course, far away, the valley has got a greater height. In between, you have this ridge, this saddle point. And then it continues. You can go from 3 images to 5 images and so on. Okay. So this is just a kind of preview, if you like, for those who are interested in looking at the general case in 2 dimensions with no particular symmetry. There's even some interesting higher mathematics here, because I mean, when a physicist says higher mathematics, it means, I guess, anything done in the 20th century, right? It's very old for mathematicians. So there's a Morse theory which tells you about the maxima and minima and saddle points of functions. And then there is a catastrophe theory which tells you that as you change over, say, from this to this, you're creating a pair. Here you're creating one more pair. Right? So when you're changing the number of maxima and minima. So there's one step beyond Morse theory. This is called catastrophe theory. And since condensed matter theory was mentioned, of course, a very elementary example is Landau theory of phase transitions, where at a high temperature, maybe you have a unique minimum of the free energy, and then as the free energy function changes, you can develop multiple minima or even a ring of minima, things like that. So since this is going to be a tour of different topics, I'm now switching to wave optics. And here the basic theme will be resolving power, and how resolving power has steadily increased, and in a somewhat unlikely way. The best resolution seems to be occurring at the longest wavelengths, the radio wavelengths. Okay, so please apologize for this very elementary figure. So let's say we first think of it as a telescope. So you have either a plane wavefront or parallel rays coming to a focus. But now you ask the question, if it had come from a different direction, you would get an image, a diffraction pattern here, and that might overlap with this one. So long ago, Rayleigh said that I would like a situation in which the image due to the second object has a zero intensity, where you have a maximum for the first object. It's a somewhat arbitrary criterion. So one way that could happen is this phase difference between the wavefront of one of the objects and the wavefront from another object. Suppose it accumulates to one entire wavelength by the time you cross this aperture. Then it's a standard trick in optics textbooks. You say, okay, so for every place where you have some phase difference, you have another place which is 180 degrees out of phase. Right? So the net result is, although the phase difference winds continuously between 0 and 2 pi, and you essentially get cancellation. So that means this tilt should amount to a distance of lambda over a diameter of d. I mean, it's strictly true for a rectangular lens, but we'll just live with that. So that's the origin of the famous lambda by d. Okay? But actually, the same figure can also be used for a microscope, but you have to kind of think of it in reverse. You have to think of the object here, right? And of course, have adjusted the microscope in such a way that this is parallel, and then later on, you could send it to a camera or your own eye or an eyepiece, right? So of course, in a microscope, you don't state its resolution in terms of angle, right? Because this angle translates into a distance on the focal plane, right? So angle into f.
So Radharam,
Yes.
may I interrupt? Can you switch on this stove sharing so that it can
Hide.
It should
Oh,
be
hide. Okay, hide.
Hide.
Oh, sure. Yeah,
okay.
thanks.
Sorry.
No,
Okay,
I didn't realize it's visible there. The zoom somehow hides it, but yeah. Okay. So the same formula, lambda by d, if you just multiply it by f, that gives you a linear resolution for the microscope. Okay. Now this is the Rayleigh way of thinking of a microscope. So a telescope is lambda by d, and for a microscope it's lambda by d into f. But this f by d over f ratio, d over f is the angle, right? Subtended by the objective lens at the focal plane, or lambda divided by the angle. I mean, these are all very rough formulae. We do better ones in proper optics course. But this already tells you why you pay so much more for a microscope with a very small f over d ratio, right? A large value of alpha, which is of course harder to make, right? Good lenses with large value of alpha. We won't say much about microscopes from now on, except that actually, I think a very different and sophisticated way of looking at resolving power was given at the same time as Rayleigh, but it was given in a factory in Jena, Carl Zeiss factory, and perhaps that gentleman was, he was not a lord or anything. So, but we should really be teaching this as well, right? This is Abbe's theory of the microscope. So he said, let's think of a grating placed at the microscope, a set of parallel wires. And we can ask a question, will I see them as parallel wires in the image, right? So his analysis was quite clever. Say that you have some wave coming in. This is a diffraction grating. You get a zero order, you get a first order, minus first order. Let's say they all fall on the lens. And then, depending on how you want to do things, you focus them. In this case, you want a magnified image. So you focus it somewhere here. And what you can see is because the angle between these orders has decreased, the spacing of the fringes in the focal plane has increased. So that's magnification. But this also tells you when you will completely fail to see the grating on this side. If these two diffracted beams miss the lens, right? If the grating is too small, right? Then they will miss the lens and then you won't see anything. And of course, he actually did experiments to prove this, okay? With gratings. And so this is the condition. And it gives rise to the same condition. Now, the lesson for us is that it sometimes helps to think of resolving power in some kind of Fourier space. You have a periodic object here, and it has, if the periodicity is too short, right, then your lens will not be able to resolve it. Okay. Now, this is causes serious problems for radio astronomy, right? Lambda by D. So here is the biggest D that we know of today. It used to be a telescope in Arecibo, United States. Many of you may know that that collapsed. Well, it is a very long-lasting mechanical structure. About the same time, this telescope, which is actually slightly bigger, came online in China. It's 500 meters in diameter. But still, if you take a wavelength of a few centimeters and divide it by 500 meters, you will get a decent resolution, maybe that of the human eye, right? And clearly, astronomers are not going to be satisfied with that. Okay. So this is about as far as building a single large diameter aperture has gone. Right? And clearly, in optical, you would not want to do this, though people are planning a 42-meter telescope, which is still staggering. Right? The Europeans have a project. Maybe it'll take a decade to come up, and that will be at a wavelength of half a micron or so. But one person who overcame this problem is Michelson. So this is a kind of very schematic representation of his contribution. It's actually a paper by Michelson and Pease, 1930. They used a Mount Wilson telescope, which is only 2.5 meters in diameter. But then they attached something like this to it. I'll show you a picture of the actual apparatus a bit later, right? And they picked this star called Betelgeuse because people had a rough idea of what the angular size of Betelgeuse might be from the temperature. So then they could use the black body formula and say if we knew its size, then how much radiation would reach us. For that, you have to know the distance. But that was a very rough estimate. He actually wanted to measure it. Okay. So this is his setup. So light from Betelgeuse fell on two mirrors, which are 6 meters apart, actually bigger than the diameter of the telescope. But these two mirrors were placed so that the telescope, I mean, this is not exactly what happened. The telescope combined the beams, but it's certainly true that Michelson looked at it. And he looked at the fringes. And the basic idea is as follows, and actually it was given earlier by Fizeau. It's not original to Michelson. The fact that, of course, if you have a point source, you'll see fringes. But if you have an extended source, the fringes could get washed out. Now, instead of lamenting that, we could say we keep increasing the separation until the fringes get washed out, and that tells us the diameter of the source. So and in this way, he was able to achieve angular resolution of some 20 milliarc seconds, and thereby directly measure the diameter of Betelgeuse is 50 milliarc seconds. Okay. So just to remind you, arc second is 5 times 10 minus 6 radians. So it's pretty small angle, right? Because so this is the Michelson interferometer. So just think of the two mirrors and the light from these two mirrors being combined. So, and let's think of a point source first. So the point source, if it was exactly symmetric between the two mirrors, you would get constructive interference. So this direction gives you constructive interference. Then you keep moving away in the sky, and then at some point the phase difference will be 180 degrees pi, and the dashed line shows the position of objects, which will give you destructive interference. Then again constructive, then again destructive, and so on, right? So you could have now an extended object, which you think of as some brightness distribution. It's a function of theta, and depending on the value of theta, you will either get constructive or destructive interference, right? Because the path difference, and the path difference is exactly what is sitting here in this formula. So Michelson called this the visibility of the fringes. Okay, and you can see it's nothing but a Fourier transform. Apparently, Michelson was not very fond of mathematics. So his papers do not actually say it's a Fourier transform, but anyway, we would all recognize. So theta is the variable in the sky, and the conjugate variable is this b, which is the baseline. Okay. Now, of course, Michelson had some values of b, but if you really want to map something in the sky, you need baselines of all lengths and in all directions. Then you can complete this Fourier transform. Right? Now, meanwhile, something very interesting happened. People were interested in measuring the angular size of other stars, which are not as big as Betelgeuse. Betelgeuse is an exceptional star. In fact, you might have read the rumors that it was going to explode, but it had decided not to explode, right? It just happened to be some dark spots coming in front of it or on the surface. But more normal stars, which you would want to study, their angular diameters are smaller. So you have to go to larger baselines. And even Michelson setup, people found it very difficult to reproduce his results soon after he passed away. So then a rather remarkable idea came into being. So just to explain that, let's just ask, what do we mean by non-monochromatic light? So you have a range of different frequencies. You have a spectrum, which is a function of a frequency. And thinking classically, you're superposing these waves, and they have random phases. And I mean, on an average, the square of the amplitude is given by this spectrum, which could be a blackbody spectrum or any other spectrum. It could even be a spectral line, right? So this is our model. Now, if you actually superpose these frequencies, please forgive the artist impression. This is the time axis, and I've just drawn what you might get, because these different frequencies sometimes interfere constructively, sometimes destructively in a somewhat random way. Of course, there would have been only two frequencies which have got nice beats, but since you have many frequencies, you get this kind of pattern. You can think of it as a number of wave packets if you like. But what we are interested in and what was exploited by astronomers is the fact that you have an overall variation of intensity, right, of this wave. Okay. Now, the interesting question which was raised by two people, Hanbury Brown and Twiss, in the 1950s, in the context of radio astronomy, was you could do interference of this waveform. For that, you would have to, be very careful in keeping track of all phase differences introduced by your instrument and so on. But could we do interference on this pattern? That is the question they raised. And I won't go into the theory. But if you think of these as beats between the multiple frequencies, let us say, as in the Michelson Interferometer setup, you would get some fringes, some coherence between the light reaching two different points. Then the claim of Hanbury, Brown, and Twiss is even these patterns will show some coherence, right? Because there are similar waves which are interfering in a similar way. I mean, that's a very non-mathematical way of looking at it. Mathematically, you would write down the effect of the Michelson Interferometer as the interference between two electric fields, so E1 and E2, and since you want the phase difference, it will be E1 star E2. whereas this one would be E1 star into E2 star. I mean, I haven't even written that out because this was supposed to be a popular lecture. But those who work with random processes know that E1 star into E2 star will have one term which is E1 star into E1 star E2. So the information in the Young's interference pattern gets squared when you do interference of the intensity. All this was absolutely fine in radio astronomy, right? You're dealing with classical waves, no problem, right? And this was actually used to solve an important astronomical problem in the 1950s. There was a very bright radio source, was the first to be found out, called Cygnus A. And not many people know that Professor M.K. Dasgupta, who had come over from the Institute of Radiophysics and was working in Manchester, he and Jennison actually were the first people to show that these powerful sources were actually double. Right? Now, this was fine. So the trouble started when Hanbury, Brown and Twist said, look, you can't have something happening at radio wavelengths and not happening at optical wavelengths. So let's look at correlation between photons received in two separate detectors. And this is a rare case where some of the best physicists contested this. They said it's impossible. Whereas these two people who were, in some sense, professional astronomers coming from the radio side, of course, they did work out some theory for the photons, but they also did an experiment. And then the controversy ended because they proved, and then various theoretical physicists said that this is happening because photons are not really independent. They are really Bose particles. So these intensity fluctuations are places where you are likely to find two photons, and then they are correlated, and one of them can fall on one detector, one of them can fall on the other detector. Again, apologies to people like Subhash who understand this much better, right? So then they went ahead, and now they could go to larger baselines because they didn't have to have very accurate control of phase. They were only looking at correlation between photons. They could build large mirrors, not of optical quality, just to collect photons. And for the first time, so the astronomy is that the temperature of these main sequence stars could be measured. I thought I would show you a picture of their. But the history is interesting. Their experiment was successful. But the whole world, including Hanbury, Brown and Twist, went back to Michelson because technology had improved. We'll see that in a minute. But here is their intensity interferometer. So this is optical interference occurring on a grand scale. Right? These mirrors are some 8 meters in diameter, but they're not very expensive. It's not like building an 8-meter telescope. They just collect the light, point to the star, and they collect the total number of photons coming from the star. You're not forming an image or anything of that kind. And then you, of course, you have cables taking you to the central thing. You can move them on the railway track, get different values of B. And of course, they had to collect a very large number of photons. The experiment ran for a long time. But in the end, people went back to the Michelson Interferometer. So here is Michelson's own. So this is the 6-meter beam sitting on top of the 2.5-meter telescope, Michelson and piece. Right? So these two mirrors, and then there are two more mirrors, and goes down to the telescope and then gets combined to the eye of Michelson. Now the same observatory, Mount Wilson Observatory, this is that dome. People have now put a large number of small telescopes, and now the technology is much better. They can actually carry the light along optical fibers. They can equalize the paths. They can record the fringes electronically. So this is a reasonably successful. And now because they're able to go to much larger values of B, 330 meters in this case, some of the best results on main sequence stars are coming from this. Okay. So this is back to Michelson Interferometer in some sense. So now the talk will zigzag back and forth in time. So now I'm going back to radio astronomy and to this Nobel Prize winning concept of aperture synthesis. Okay, so this is the North Pole, this is the Earth, this is Cambridge, and this is a railway line which is running east-west, and these are just two telescopes. Okay, so following Michelson, one could look at the interference of the signals received by these two telescopes. And in radio astronomy, interference is not that difficult. You can use cables, you can You can record the signals if you like, and you can superpose them electronically. And now you do have the freedom to change the separation. Of course, the source should not have changed. So that function b of theta should remain the same, but you keep changing separation. And then the other beautiful idea is that you can also change the direction, especially if you're looking at the North Pole, because the Earth rotates. Okay, and this works so long as you're not on the equator. It works reasonably well. So the idea is that, so a simple way of thinking about it is in reverse. So imagine that these two telescopes were sources of radiation. They would produce constructive and destructive interference in the sky. And depending on where the source was, the source would receive either maximum intensity from these two radio transmitters, or it would receive minimum intensity, right? Zero intensity. And one of the sacred principles of optics is reversibility or reciprocity. So it works the other way also. So if the source happens to be here, you get constructive interference. So radio astronomers keep talking of fringes in the sky as if they were actually transmitting radio waves, but they are only receiving them. Okay. So here's a picture of that railway track in Cambridge I told you about. And this is Martin Ryle, who received the Nobel Prize for both developing this technique and using it. So for example, this double source, which was barely seen to be double by Jennison and Dasgupta. So by the time Ryle and his colleagues were able to map it fully in 2 dimensions, measuring the Fourier transform, of course, a very tedious process of moving these telescopes, taking new readings and so on, they were able to get a lot more physics out of it. That what these bright sources were, there was a central spot which was feeding energy, but all that is astronomy. Okay, I want to focus on this technique of aperture synthesis. Okay. So after this, Cambridge had a 5-kilometer telescope, but pretty soon people with more money overtook Cambridge. So in the United States, the very large array was built. It had 3 railway tracks, and they were now at 120 degrees. So you did not have to wait for 12 hours. In 8 hours, you would have got the rotation which you need. This was built in 1980s, whereas the work of Martin Ryle was 1960s. So it took a while. Right? But the length of these arms now went up to, the maximum separation was now 30 kilometers. And you need that because you're operating at radio wavelengths, right? So to get more resolution, you have to separate the 2 elements of your interferometer. And then, of course, they could afford a larger number of telescopes, 27 telescopes. Okay. But in spite of all this, you don't really fill in the full Fourier transform. Okay. Well, you could if you kept moving these, but people quickly found that you don't need it. For simpler images, at least, you could have algorithms for forming an image from incomplete Fourier transform. Now, this is not really rigorous mathematics. It's somewhat heuristic, but it's very successful. So this particular telescope, very large array. Now, by the time you are separating telescopes by tens of kilometers, you have to worry about the phases introduced by your instrument, by the ionosphere, or at high frequencies, even water vapor in the atmosphere. So then you need algorithms to correct that. So a lot of progress occurred in radio astronomy. I mean, we are now talking of decades of work. And then people said, let's increase the baseline to thousands of kilometers. Okay. In this case, you have to record the signals. You can't connect these 2 telescopes in real time by an optical fiber or a waveguide. Okay. And then you do the interference. Okay, the spelling is wrong, but in playback, you play back the tapes. So this technique is called very long baseline interferometer. So people kept going to higher and higher resolution. So now you could have one telescope in Hawaii and in the United States, and the Europeans again had their own network, which went all the way up to Russia, and occasionally even when I think Chinese telescope would join in. Because VLBA experiments are complicated. All the telescopes have to work, you have to coordinate. They were not built for this purpose, right? But and ultimately you would have to go to shorter and shorter wavelengths to improve the angle. So I'll straight away fast forward to the most spectacular achievement. So before that, two pictures of the VLA, because it's pretty beautiful. Right? I mean, it looks very flat, but actually it's several thousand, 5,000 feet above sea level. Another view of the same telescopes. Right? But the best astronomical resolution ever achieved, and this is only a few years ago, I've given it in radians. I've given it in arc seconds. So the radian figure you can easily get by dividing the wavelength, which is 2.6 millimeters. So it's really millimeter waves, right? Which are highly absorbed by the Earth's atmosphere. I mean, people who have been in Raman Institute would know that.
Something has happened. It's frozen, I believe.
It's frozen, I think.
Some problem from his side.
Splitting around, getting very hot, radiating in the entire electromagnetic spectrum.
Professor Rajaram.
Yes, sir.
You are disconnected for, I think, 10 or 15 seconds.
Okay. If it's only seconds, I don't mind. I'll go back. Right. Am I connected now? Okay.
Yes.
So was this there?
Yeah, this was there.
So I was just remarking that this was announced in 2019, I think, right? The image of the black hole in M87, but I'm just focusing on the angular resolution, which is some 10 minus 10 radians. So even arc second is already considered a brilliant resolution, but this is 10 minus 5 arc seconds, right? And that was achieved by the wavelength being 2.6 millimeters and the separation being up to 10,000 kilometers, okay? And this is the headline grabbing image. The evidence for the black hole is that all this matter which is emitting radio waves is in some kind of ring around the black hole, but you're missing the radiation which has fallen into the black hole. Of course, that's just English, but a lot of modeling has gone into it. And it's also nice to look at the collection of telescopes, right? So here's the Earth, here's one in Spain. These are all millimeter telescopes. So they were built long back to study interstellar molecules, which is a completely different story. So here's some in Arizona, one in Hawaii. You can see that as the Earth rotates, there are only a short period in which both Hawaii and Spain can see the same source. This source is the northern, it's 12 degrees above the celestial equator. So the South Pole doesn't really see it. But when they look at a calibration source, the South Pole telescope sees it, Chile sees it. So the people behind this experiment had to work for almost 10 years to install receivers, hardware, software. These telescopes belong to different people. They had to persuade all of them to join in this experiment. So the final paper has 347 authors, of which I think at least 4 had passed through the Raman Institute. And some had worked on millimeter waves at the Raman Institute. But of course, they've all moved on to other places. So here are all these millimeter telescopes, right? And in this case, the coverage is quite incomplete, right? Because there are large gaps between the telescopes. So a lot of modeling of the source and a lot of the kind of algorithms I told you to make images also went into this. Okay. So this project, in case you want to look up more, is called the Event Horizon Telescope. It's led by these 2 institutions. You can go to the website of either of them. Center for Astrophysics in the United States, Max Planck Institute for Radio Astronomy in Germany. Right. So having spent time in NCRA, although we didn't operate at millimeter wavelengths, I thought I should devote some time to the work going on there, which is not the highest angular resolution, but has its own interesting features. Okay. So that group started this is a very schematic representation of radio waves at a wavelength of 1 meter coming from source. And this is the UTI radio telescope. I'll show you a picture of that later. So you could think of a plane wave, and the part that hits the moon, of course, it doesn't come to you. So it's as if you have a diffraction by a straight edge. That's so this plane wavefront is blocked, and therefore you get fringes. And the fringes are not equally spaced in this case. All of you know that the reason is that one way of looking at it, and it goes back to Young. We don't teach this because Young was a very intuitive thinker. So the usual way we teach is the Fresnel way, which you do an integral over this surface and evaluate the integral either here, in which case it gets heavily damped, and when you come here, the integral oscillates. Right? They're Fresnel integrals. But Young suggested that we can also look at it as interference between this direct beam and a wave coming from the edge. And when you come into the shadow, you get only the wave coming from the edge. And the nice thing about this simplified way of looking at it is that the path difference is d into 1 minus cos theta. So it's approximately theta squared. So the fringes are equally spaced in theta squared. Now, this technique was used by radio astronomers. Occasionally, the moon would cover up some important radio source. But I think it's Professor Govind Swarup who made an industry of it in some sense. He still had to build a large collecting area. It was built on this hill slope so that it could be rotated about this axis, which is parallel to the axis of the Earth. The radio is focused on this thing. So this whole thing is 500 meters long. Okay? And therefore, this had enough collecting area to see even faint sources. But you didn't. Of course, the resolution of this telescope was not great. Okay? But when it operates as an interferometer, if you think of it as interference between these two beams, then the resolution is set by the baseline. Right? So if you're able to detect the fringes well after the source has come out from the edge, you will get better angular resolution. So they were able to achieve angular resolutions of a few arc seconds at a wavelength of 1 meter, which normally would have required a much bigger aperture. So this was quite ingenious. At that time, VLA and so on had not come. Okay, so this was how the group began. But pretty soon, they went on to this ambitious project, which is aperture synthesis. Right? But the whole idea was to do things which were more difficult to do elsewhere in the world. So this group continued to operate at meter wavelengths. And there was a very interesting reason for operating at a wavelength of 1 meter. A lot of astronomy is done at a wavelength of 21 centimeters because that is where a hydrogen atom in its ground state, which is slightly split by hyperfine interaction, will radiate, emit or absorb. So if you want to study hydrogen atoms nearby in our own galaxy, you build receivers at 21 centimeters. And this had been going on from the 1950s. But if you want to study hydrogen in very, very remote galaxies, then the expansion of the universe will shift that to meter wavelengths. And this was the ambition of Swarup and his colleagues. These are very faint, but the advantage of working at longer wavelengths is that with a lot of ingenuity, and they could build telescopes which were relatively light, relatively inexpensive compared to what is done elsewhere in the world. They are not on railway tracks. They are on these, right? So clever distribution of antennas over the countryside in Western Maharashtra, near the town of Narayangaon, was arrived at. And I can't claim credit for any of this because by the time I joined in the year 2000, this project was essentially complete. Okay. So here's another view of one of the telescopes. I just wanted to show this. It's rather beautiful, right? And it operates not just at 1 meter, but it can operate even at 21 centimeters. Because having built such a large telescope, why not use it at 21 centimeters as well? And a lot of interesting science has been done. And of course, a lot of other objects, like these radio galaxies, which I told you about, pulsars, have all been studied. And now these observations have been going on for 20 years. So this is a picture of Professor Govind Swarup, taken when he was much younger. He passed away in September of last year, right? And certainly he was the driving force. But in fact, his first generation of students themselves, joined this project and in turn attracted many other talented people, including engineers, by the way. You need very good engineers because this is not routine engineering, right? Building these, maintaining them. So I just want to show one scientific result from this telescope. And the reason is that it's recent. It appeared in October of last year. And it goes some distance towards Professor Swaroop's dream of observing this 21 centimeter emission. And now this is at a wavelength of 710 megahertz. So you're sufficiently far away in the universe that the wavelength has got doubled by the expansion of the universe. So this is a region where we didn't have much information about how much hydrogen is there in galaxies and so on. So these galaxies could be observed with, for example, the Hubble Space Telescope and so on. But these were now observed with GMRT, right? But a single galaxy would be too weak to give you any signal. So what was done was the signals from 7,000 galaxies were combined, and you would gain a factor of square root of 7,000. And finally, this signal has emerged well above the noise. And this was a sufficiently important result. One of the first results telling you that there was more hydrogen in these galaxies in the past than there is today, and also making it quantitative. Okay, so it's a very nice result. And I like to compare it to something which some of you may have seen, right? So do you recognize these people? You probably should not, because this is supposed to be the average in you. Okay, so images of a large number of males, young males and young females were taken. Of course, they had to be scaled a little bit so that the spacing between the eyes and all that. And then they were superposed. So that's exactly what is done here. So in radio astronomy, this is called stacking. I don't know what it is called here. I just picked this up from the internet. Anyway, they seem quite pleasant people. Okay. So the last thing, and forgive me for again coming back to GMRT, but I spent 10 years there, is that again, very recently, early this year, the Institute of Electrical and Electronic Engineers, IEEE, recognized the building of the GMRT as a milestone. And the two previous ones from India, and I have to say they are giants, is Jagdish Chandra Bose, who incidentally worked with millimeter waves, and then the world forgot millimeter waves for a century, and then came back to it. I mean, he worked at 40 gigahertz, I think even 60 gigahertz, which is amazing. And then the discovery by C.V. Raman. So these were recognized by IEEE, because IEEE includes optics in it. And the GMRT, so they, I mean, there was a rigorous review of whether it deserved this recognition or not. And there was a function and there was a plaque which said all this thing. So just to tell you that this story of novel optical techniques has our own contribution as well. So thank you very much. Exit. And maybe I will just keep the presentation on in case, or I can go back to it in case it's needed to. I do hope there are questions. And where am I?
Thanks for the wonderful talk, Rajaram. I mean, it was, I think, extremely engaging. So if there are questions, we can take some questions.
Professor Vikram.
Yeah.
I had a question about the gravitational lensing.
Yeah.
What I understood is there are two effects there. One is the gravitational time delay and then the geometric time delay.
Yes.
Right? Yeah, the geometric time delay would depend on the refractive index.
Which is essentially one.
Yeah.
It's essentially one because these are traveling over cosmological distances. There is.
So, okay.
Yeah.
No, then how we, what is the geometrical time delay then? I don't understand.
So literally, okay, can I do one thing? Can I share screen again? Let me do that. Oh, I'm already presenting. Okay, so good. Yeah, let me draw a sketch. Maybe the geometric time delay was a very complicated way of stating it. So we have a source. In fact, let's not put any gravitational lens. So this is the wavefront coming from the source, right? And this is the observer. Okay. And we are looking at a number of paths. Right? This is the direct path. Okay. But in principle, we could imagine paths going like that, yeah, which are longer. And that's what Fermat's principle tells you. Now, if you ask how much longer is this path compared to this path, the simple geometric construction would be to draw this dashed thing, right? Right. So up to this front, all rays have traveled equal distances. Likewise, from this front up to O, all the rays have traveled equal distance. So excess path is just between these two wavefronts, right? And in the simple geometry, and there's the spherometer formula which tells you that the clearance between these two spheres is just I don't know, it's I think theta squared. D squared by 2 into 1 over R1 plus 1 over R2. Yeah, this is the spherometer formula. So that is the geometric time delay. So there's no mystery about it. But what can happen is the image this may not be the shortest path once you introduce, or may not be a stationary path once you introduce some extra time delays. Right. So yeah. So maybe the terminology was yeah.
Professor Kulkarni, you can
Yes.
answer.
Yeah, just a question. Maybe it's not very important, but do you also consider relative motion between the observer and the source? And would that in any way affect the optics?
Yes. Answer is yes. And I glossed over that point in my very first slide, which I will go back to. Yeah, this one.
Yeah.
The reason why the intensity is changing is because of the relative motion between the observer who is on Earth. And so you're absolutely right. So it's as if you're exploring different geometries. And some geometries give you a higher intensity and some geometries give you a lower intensity. So that's what's happening. Of course, I'm not telling you the quantitative behavior of these curves, but your point about relative motion is right. But it's also true that when you come to examples like this one, which is on a galactic scale, or the arcs, then because the scales are so much larger, within human lifetimes, you wouldn't see this. However, there is a phenomenon called microlensing, which is again relative motion. So these images can change in intensity because in this galaxy, some individual star can pass in front of this and create effects like this. So yes, relative motion is quite important, and thank you for bringing it up.
Are there any questions? So I have a question, Professor. Yeah, I mean, just for the students, maybe some of them. So, could you just again explain a little bit more about the case when you looked at interfering multiple frequencies, and then you had like a fringe, like there was a time series.
Okay. Yeah, I could.
Yeah. How did the envelope, the overall intensity distribution? Yeah, just that point. Could you just illustrate on?
Okay, so let me say a few. Yeah, I think one can be more mathematical here. So it's as if your E of t is a summation of over different frequencies, and amplitude, which is a function of omega. And I mean, one uses the complex thing for convenience, right? So this also is a complex amplitude. Or one can have this as a real amplitude, and then of course you have to put a phase which is also a function of omega, right? So this is EFT. Now, of course, one could. By the way, I should have done this. I could have just made a plot of the real part of this, taking a few values, and that could have illustrated it. But that's not a proof, right? So if one wants a proof of how this EFT fluctuates, one looks at a quantity called I've written a formula, but let me explain it in the following way. That in fact, the best way to thinking of this object is again the famous Michelson Interferometer, right? So let me, So this is a half-silvered mirror. This is the source. So this EFT comes in here, goes, bounces off, comes back, and another part of it goes, bounces off, comes back. But the two parts may not be equal, right? So it's as if you're interfering E of T plus tau with EFT. So if you do that calculation, this becomes, I'm not doing the calculation. And of course, this should no longer depend on T, right? You can average over T. So then this becomes a summation of A square of omega. Because of this star, these 5 omegas and all disappear, but you do get an e to the minus I omega. So this tells you that this interference pattern will be a Fourier transform of this one, which is called the power spectrum. So I think if the Michelson interferometer experiment is one of the standard experiments that people do, of course, if you do it with a laser, you will see fringes, no matter, for all the path differences accessible in the lab. But if you do it with sodium light, as you move the mirror even by a few millimeters, the fringes disappear, right? So that's because this A square of omega is a function like this, right? And if you look at its Fourier transform, it comes down. So maybe that's a slightly more mathematical explanation of, but the physical explanation is that the moment you're interfering a number of frequencies, you get this kind of wave packets. Yeah, I think maybe that word wave packet, I don't know if I use, but you can think of. Yeah. So by the way, because I'm sure people would want to look it up. So this is a theorem which has nothing particularly to do with, of course, Michelson knew this theorem, but it was made into a proper mathematical theorem many years later. And it goes by the name of Wiener-Khinchin theorem. And I think one of the finest books for people interested in optics is something called, in fact, there are two books, both by the, one is called Statistical Optics. Of course, they're very detailed books, but if someone wants to go deep into it, and there's another book called Fourier Optics. And both are written by, this is actually his name. I'm not telling you that he's a good man. Yeah. So So basically, this idea that, so this is a measure of the fluctuations in some sense on a time scale of tau.
Thanks. Yeah. Are there any other questions from any of the students or any of our colleagues? Okay, so I'll over to Professor Chaubey.
Okay, so again, on behalf of the physics department, we are grateful to you for such a nice talk, and we all are benefited with this talk. And in future, we would be happy to welcome you in Pilani physically. So hope that the COVID situation will be improving in the near future, and we would be happy to welcome you in Pilani.
And Goa as well.
I was going to no.
So
Pilani includes Goa, no? It's Bits Pilani, Goa, and Bits Pilani.
Yeah, Bits Pilani, including Goa.
Pilani is delocalized.
Yeah.
Okay. Thank you very much. It was a pleasure to meet new people and see old friends as well. Thank you.
Thank you, sir. Thank you very much.
So with this lecture, we end this online series. So let me briefly tell about this online series. So in this online series, we had 6 speakers, including you. So it started in March, and the first lecture was given by Professor Balakrishnan on this interesting quantum mechanical aspect of very simple problem, a particle in a box. And then it is followed by Professor Patrick Rinke, who talked about the machine learning aspect in solid state physics. And later on by Professor Giovanni Stepney, who talked about the visualizing of electron correlation in coincidence experiments. And later on, Professor Gautam Singhvi talked about the interesting problems related to biology, physics, and computational aspect from the interdisciplinary perspective. And before you, Dr. Didier Sebiu from France, he talked about the memory function approach in solid state physics. So we had a lot of different type of talks in this online series. And I would like to thank the entire department who have supported me, the research scholars. But I would like to name a few of my faculty members who were actively participate in this online series. Professor Jayendra Bandopadhyay, and then Professor Tapomay Guasarkar, Professor Naveen Singh, and Professor Manjula Devi. So these all faculty members were part of the organizing committee. And I would like to thank one of the research scholars, Chandrachud. Chandrachud is there?
Yes, sir, I am here.
So he took all the pain of preparing the posters, the nice posters for the advertisement of various talks. So I would like to thank Mr. Chandrachud for his lot of efforts in this. And of course, at the end of the day, the Department of Physics and the students, the PhD students, and of course, all the speakers who delivered the wonderful talks during this online series. So that is from my side about this online talk series. So Professor Rajaram, you want to say something before we discuss?
I think I already said that even before the talk began, we were chatting that I enjoyed my visits to Pilani, and yes, one can always hope for future in-person visits. But thank you.
Okay. Okay. Anybody in the audience who wants to say something?
Okay, then I will disconnect.
Okay. Okay. So we can disperse.